Welcome to Spaceverse, your portal to cosmic adventures. Imagine this, a mysterious object hurtling through space, millions of kilometers away, yet on a trajectory that will bring it through our cosmic neighborhood. In recent months, astronomers have been buzzing about the James Webb Space Telescope capturing something extraordinary, a large interstellar object, traveling from a distant star system passing through our solar system for the very first time. Early claims suggested it was 10 light-years out, moving toward Earth, even hinting at trajectory shifts, but the real story is far more profound. This visitor is known as 3I Atlas, an ancient interstellar comet that has wandered the galaxy for potentially billions of years. It's not just another rock drifting in space. It's a chemical time capsule carrying information from an entirely different stellar nursery. With Webb's powerful infrared vision, astronomers were able to see the first real images of this cosmic traveler, revealing details that challenge everything we thought we knew about comets and their journeys. The discovery began in early July 2025 when the Atlas survey system noticed something unusual against the backdrop of distant stars. This object was unlike anything normally seen in our solar system, only the third confirmed interstellar object ever observed, following the enigmatic Oumuamua and the comet 2I Borisov. Each of these visitors had already rewritten the rules of what can drift into our cosmic backyard. Oumuamua defied classification with its strange shape and acceleration, while 2I Borisov, though clearly a comet, left questions about its chemical origins unanswered. 3I Atlas, however, promised something entirely new. Traveling at nearly 210,000 kilometers per hour on a hyperbolic trajectory, it's a one-time visitor, a messenger from distant stars, destined to continue on its lonely journey through the void after its brief encounter with the Sun. Unlike comets formed in our own system, which follow elliptical orbits, 3I Atlas's path guarantees it will never return, making these observations unique and fleeting. Capturing this fast-moving target was no small feat. Webb's near-infrared spectrograph had to lock onto a faint, barely perceptible speck of light against a shifting sea of stars. From its perch at the second Lagrange point, Webb's team performed precise calculations to ensure the comet would fall perfectly within the telescope's field of view. Every pixel counted, as the goal wasn't just a photo, but a complete spectral map of the comet's glowing coma, the hazy envelope surrounding its nucleus, revealing the materials composing this interstellar traveler. The results were astonishing. Webb's infrared instruments revealed a dense, carbon dioxide-dominated coma, radiating in wavelengths between 0.6 and 5.3 micrometers. This is not merely a beautiful image, it's a document of cosmic history. Within that ghostly glow, astronomers detected water vapor, carbon monoxide, water ice, dust, and even trace molecules like carbonyl sulfide. Each one carries a clue about the comet's origins, its chemical evolution, and the unique environment of the star system where it formed. Perhaps the most striking discovery was the overwhelming dominance of carbon dioxide. In 3I Atlas, the ratio of carbon dioxide to water is roughly 8:1, far higher than any comet observed in our own solar system. This suggests a vastly different formation environment. While comets in our system usually outgas water as they approach the Sun, creating familiar glowing tails, 3I Atlas behaved differently. Its weak water signature hints at an insulating crust or internal structure that slows heat penetration, allowing carbon dioxide and carbon monoxide to dominate the observed activity. This chemical fingerprint is a direct record of the comet's birthplace, possibly near a carbon dioxide ice line in its parent stellar system. The unique mix of dust, gas, and ice in its coma paints a picture of formation conditions far removed from our own Sun's neighborhood. Despite the harsh conditions of interstellar space, 3I Atlas has retained significant chemical complexity, a testament to its resilience during its long voyage through the galaxy. Webb's images also revealed clues about how the comet emits gas. Rather than isolated jets, the outgassing appears broadly across Sun-facing regions. This suggests a porous or highly active internal structure, with multiple areas contributing to its glowing coma. Understanding this spatial distribution helps scientists unravel the comet's internal mechanics, shedding light on how it processes solar energy and maintains its structure while traveling at incredible speeds. Even determining its size is challenging. Estimates place 3I Atlas's diameter between 1.4 and 5.6 kilometers, which affects surface area, thermal behavior, and outgassing patterns. Despite a substantial coma, it exhibits almost no measurable acceleration from gas recoil, unlike typical comets, whose jets can nudge them off course. This hints at a massive or highly cohesive nucleus capable of resisting the subtle forces created by escaping gases, possibly one of the most massive comets observed, with an estimated mass exceeding 33 billion metric tons. Its hyperbolic orbit confirms its interstellar origin, coming from a general direction near the constellation Sagittarius. Yet tracing its exact birth star is nearly impossible after potentially billions of years wandering the galaxy. Another puzzle, activity begins unusually far from the Sun. Most comets remain dormant until reaching Jupiter's orbit, but 3I Atlas shows early outgassing at much greater distances, suggesting volatile ices that sublimate at low temperatures and hinting at unique surface or internal composition. All of this makes 3I Atlas an unprecedented scientific treasure. It offers a rare glimpse into materials formed around another star with properties that expand our understanding of planetary formation and chemical diversity in the galaxy. For astronomers, it's both a challenge and an opportunity to decode the story of an object that has survived the void for billions of years, carrying secrets older than our solar system itself. As we follow its approach, the anticipation grows. Webb's observations mark the first time we can study such a visitor in such detail, bridging the gap between interstellar wanderers and the history of our own cosmic neighborhood. Every infrared pixel, every spectral line, is a piece of the story, one that hints at the extraordinary complexity of the universe and the surprises still waiting beyond our solar system. Some travelers are older than the stars in our sky, and 3I Atlas, also known as 3I Atlas, may be one of the oldest. Estimates suggest this interstellar comet could be anywhere between 3 and 11 billion years old, potentially predating our entire solar system. If these numbers hold true, 3I Atlas is essentially a frozen relic of the galaxy's earliest epochs, carrying within its icy heart chemical memories of environments that existed when the Milky Way was young. Back then, our galaxy likely looked very different from the spiral we know today, with stars forming in clusters, clouds of gas and dust scattered across a turbulent cosmic landscape, and early planetary systems emerging in ways that may seem almost alien to us now. Its speed is staggering. Moving at roughly 210,000 kilometers per hour, 3I Atlas surpasses even the interstellar visitors Oumuamua and 2I Borisov, making it one of the fastest objects ever observed in our solar system. This velocity isn't just impressive, it tells a story. To reach such speeds, 3I Atlas must have been violently ejected from its parent star system, likely through a close encounter with another star, massive planetary migrations, or the gravitational turmoil caused by a nearby binary system. These violent events may have flung it into the vast emptiness of interstellar space, where it has wandered for billions of years. Interstellar comets aren't gentle travelers, they are survivors of cosmic catastrophes, hardened by the harsh conditions of deep space. Over its eons-long journey, 3I Atlas has endured a relentless gauntlet of cosmic challenges. Bombarded by high-energy cosmic rays, pelted by micrometeorites, and stressed by thermal fluctuations from nearby stars, many smaller or weaker objects would have disintegrated long ago. Yet 3I Atlas has survived, preserving deep reservoirs of volatile compounds and organic materials that have remained essentially unchanged for billions of years. Its survival hints at a remarkable internal structure, one strong enough to withstand the rigors of interstellar travel and perhaps shielded by layers of protective ice and dust. During its journey, 3I Atlas may have drifted through dense molecular clouds, regions of space where gas and dust densities are thousands of times higher than typical interstellar space. Passing through these clouds could have added new material to its surface, altered its chemical composition, or even triggered surface reactions that produced complex organics. Some of the compounds detected in the comet's coma today may actually reflect these interstellar processing events, providing a window not only into its original formation, but also into billions of years of chemical evolution in the galaxy. Studying 3I Atlas allows us to examine primordial materials preserved from a time long before our solar system even existed, giving us a rare glimpse into the chemistry of early stellar environments. Observing such an extraordinary object requires a coordinated global effort. No single telescope could capture all the details of a comet moving at incredible speed through our solar system. Instead, scientists orchestrated a campaign combining space-based and ground-based observatories, each contributing unique capabilities. The Hubble Space Telescope captured the comet on July 21, 2025, when it was about 277 million miles from Earth. Hubble's images revealed a distinct teardrop-shaped dust cocoon surrounding the nucleus, providing key insights into how dust is distributed, the shape and orientation of the tail, and how mass loss occurs as the comet interacts with the solar wind. Meanwhile, the James Webb Space Telescope probed the comet in infrared light, detecting volatile compounds, organic molecules, and other chemicals that help scientists reconstruct the comet's history and the environment in which it formed. Ground-based observatories, including Gemini North and South, monitored changes in brightness, tail evolution, and activity levels over time. This continuous observation is essential because space telescopes have limited observing windows and cannot track every rapid change in the comet's activity. By combining these observations, astronomers created a comprehensive dataset that is unprecedented for any interstellar object, revealing both its physical and chemical complexity. Archival searches added another layer of depth. After discovering 3I Atlas in July 2025, scientists combed through historical sky survey images and found the comet weeks or even months earlier, at much greater distances from the Sun. This allowed them to extend the timeline of observations, providing insights into when its activity began, how quickly it ramped up, and how the nucleus responds to solar heating. This kind of retrospective analysis is vital for understanding the comet's thermal properties, sublimation rates, and the composition of its nucleus. 3I Atlas has also revealed unexpected optical properties. Polarimetric studies, which measure how sunlight scatters off the comet's dust, showed an unusually deep negative polarization branch, a feature rarely seen in solar system comets or asteroids. This suggests that the dust grains are extremely small, highly porous, or uniquely textured, giving the comet a distinct optical signature. These characteristics hint at a formation environment very different from what we see in our own solar system, possibly shaped by exotic conditions in another star system billions of years ago. Chemically, 3I Atlas is just as unusual. Observations from the Neil Gehrels Swift Observatory detected faint water emission, indicating sublimation of ice at roughly 40 kilograms per second, even while the comet was 3.5 astronomical units from the Sun. While water contributes less to the overall activity than the dominant carbon dioxide outgassing, its presence confirms that volatile rich regions exist beneath the comet's surface. Even more intriguing is the presence of nickel in the coma, a metallic component rarely emphasized in comet studies. This suggests that some dust particles carry metallic inclusions, perhaps formed in high-energy environments involving shock heating or metal-rich protoplanetary disks. The combination of carbon dioxide dominance, water, and metallic compounds makes 3I Atlas chemically unique, highlighting the diversity of interstellar objects and expanding our understanding of what materials and processes may exist around other stars. As the comet approaches its closest point to the Sun in late October 2025, scientists expect dramatic changes. Solar heating will trigger sublimation of new volatile compounds, potentially revealing previously hidden molecules and altering the composition of the coma. Dust and gas will accelerate, and the tail may extend dramatically, providing a spectacular display visible from Earth-based telescopes. There's even the possibility of structural changes or fragmentation as the comet's nucleus responds to intense solar heating for the first time in its long journey. Some of the most critical observations will be challenging. When 3I Atlas passes behind the Sun, terrestrial telescopes and near-Earth satellites will lose direct sight of it. Observations will rely on solar-orbiting spacecraft and indirect measurements, making pre-perihelion data from Webb, Hubble, and ground-based observatories invaluable baselines for comparison after the comet emerges from conjunction. Already, images from Gemini South show the tail growing and evolving rapidly, with curvature, brightness variations, and tail morphology revealing the dynamics of dust and gas under solar radiation pressure. These details encode information about particle sizes, velocities, and mass loss rates, helping scientists infer the internal structure of the comet and the processes that have shaped it over billions of years. 3I Atlas is more than just a visitor. It is a messenger from the distant past, carrying information about stellar formation, chemical evolution, and planetary system processes far beyond our own. Studying it provides a unique opportunity to understand how comets survive in the interstellar medium, how they are affected by magnetic fields and cosmic rays, and what they can tell us about the formation of other star systems. The comet's journey reminds us that the universe is vast, full of ancient wanderers, and brimming with secrets waiting to be discovered. It highlights the importance of international collaboration, rapid coordination, and multi-wavelength astronomy in modern science. Every observation, every spectral line, every dust grain adds a piece to the puzzle, bringing us closer to understanding the cosmos and our place within it. And that is the story of 3I Atlas, a visitor older than our sun, carrying billions of years of cosmic history and offering a glimpse into the mysteries of interstellar space. Its journey shows us that the universe is not static, it is dynamic, alive with movement, and full of extraordinary phenomena just waiting for curious eyes to uncover them. If you enjoyed this voyage into deep space, make sure to subscribe to Spaceverse, hit the like button, and click the bell icon to join us for more adventures across the cosmos. We'll continue to explore interstellar visitors, distant galaxies, black holes, and the many wonders of the universe. Thanks for watching, and as always, keep looking up.